All right. In this video, I'm gonna focus on rotational or circular motion. Okay. To understand circular or rotational motion, let's understand the analogy between linear and circular motion. Of course, this question here is basically on either circular motion or rotational motion. Okay, they are all together. Okay. Now, but before we understand this question here, before we solve this question here, sorry, before we solve this question here, we have to understand the analogy, that is the relationship between linear motion and rotational motion. Okay, let's take a solution here. Solution. All right. Let's know the analogy between linear and circular motion. Okay, you can write analogy between linear and circular motion. Okay, now let's consider the analogy here. Okay, this is my linear, this is my circular motion. Okay, we are using the parameters of linear to relate with circular. We are using the parameters of linear here, that is this linear here, to relate with circular. Okay, now let's try to know them. Okay, the first one here is velocity. So the parameter that represents velocity is either v or u. V represents final velocity, u represent initial velocity. Please take note. So in circular, we don't call it velocity, we call it angular velocity. And we use omega or omega naught to represent that. Omega represents final angular velocity. Omega naught represents initial angular velocity. Please take note. The next one here is acceleration. We use A to represent acceleration in linear, but in circular, we don't call it acceleration, we call it angular acceleration. Please take note. We use alpha to represent this. Please take note of this. So the next one here is mass. We use m to represent mass, but we don't call it mass in circular motion. We call it moment of inertia. Moment of inertia. Please take note. And we use I to represent this. Okay. The next one here is force. 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 Force is mass times acceleration. Okay. But in terms of circular or rotational, we call it torque. And we use tau to represent torque. Tau, something like this. Okay. So class, remember mass is, let's understand it perfectly. We call mass moment of inertia, that is I. That is this guy here. This is what is mass in circular. So we represent this as I. in terms of circular, we don't call it acceleration. We are trying to use this guy here to relate our formula in circular motion, okay? So we don't call it acceleration, we call it angular acceleration, and the unit is, sorry, the symbol is this, okay? That is, this is going to be alpha here. So our torque is equal to moment of inertia multiplied by angular acceleration. Please take notes. So the next one here to consider is kinetic energy. Kinetic energy, okay? That is, the formula is half mv squared. So we don't call it kinetic energy, I'll call it rotational kinetic energy. That is K E of what is equal to 1 over 2. So in place of 1 over 2 is constant, it's a value. So it remains the same both in circular or linear. But here, this one here is later though. So we have a symbol that represents mass, and that symbol is I. Or we have a symbol that represents velocity, that is final velocity, and that symbol is omega square. Please take note. So the next one here is power, that is power. The next one is power, okay? That is linear will represent power to be this. Power is force times velocity, okay? So here we call it rotational power. So let's relate. We use tau to represent force in circular. So this is tau. We use omega to represent final velocity. So this will be omega, okay? So finally here, we have linear momentum. Linear momentum, okay? And linear momentum here, class, is equal to mass times velocity. So in terms of circular, we don't call it linear momentum, we call it angular momentum. And we use L to represent this. The unit is using this relationship here to write the formula for angular momentum. Mass is I, while velocity is omega. So these are the formulas that you need to know in circular motion, okay? We use the linear motion parameters to relate with circular motion to understand the formula properly, okay? Now let's go back to the question here, class. This is the question here. They said a body of angular velocity 2 rad per second has its moment of inertia as 0.2 kg meter squared. So moment of inertia here, this guy here, moment of inertia here is given to us as 0.2 kg meter squared, okay? We're asked to find its angular momentum. We're asked to find its angular momentum, okay? And the angular velocity is given to us as 2 rad per seconds. So class, let's solve this question. Okay? Before we solve this question here, we have to list out the given parameters. Class, let's list out the given parameters here, okay? The given parameters are the first one given to us there is angular velocity, that is 2 rad per second. The second one there given to us here is moment of inertia, that is 0.2 kg meter squared. And remember, we are asked to find the angular momentum. From the analogy, remember, from the analogy, we say that momentum, that is linear momentum, was given to us as linear momentum, sorry, linear momentum P is mass times velocity. So relating this to circular or angular momentum, so that angular momentum is equal to I omega, that is I omega, okay? So we are asked to find angular momentum. We are not asked to find linear momentum. We are asked to find angular momentum. We are not asked to find linear momentum. So using this formula, L equal to I omega, this represents moment of inertia. The omega represents angular velocity. So replacing the values, we have this to be 0.2 times 2, our answer will be 0.4 in kg meter squared per seconds. Okay, so when you look into the option there, A is 0.2 kg meter squared per seconds, B is 2 kg meter squared per seconds, C is 0.02 kg meter squared per seconds. So D is 0.4 kg meter per second. So the answer is D, okay? So all you have to do here is to hit the subscribe button to get more video on angular momentum, okay? Thank you.